I'm Yaga Richter from NCAR, and a lot of the work I'll talk about was carried out by Jack Chen, who's with me here in collaboration with Chi Tang and Xiaosheng Shi and Phil Rash. A little overview of the presentation. So I'll give a brief introduction of the QBO and why it's important. And I'll talk about the QBO and E3SM and the details of gravity wave parametrization. I'll talk about the tunings we needed to make to improve the representation of the QBO and what impacts it has had on the simulation. And I'll mention a little bit about the future work that we're going to carry out with the same team. Okay, so the Quasi-Biennial Oscillation, or the QBO, is the dominant mode of variability in a tropical stratosphere. So the QBO consists of alternating easterly and westerly shear zones near the equator. So this figure here shows the zonal mean wind average between 5 south, 5 north from ERA interim reanalysis. This is from 1985 to 2005. And if you count these cycles of alternating phases, you'll arrive at a mean period of 28 months. But what's important to note that the QBO period can vary between 20 and 32 months. So it's not always 28. It's actually quite variable, but the mean is 28. And the reason this is important is not only an oscillation in the zonal mean wind, it's also an oscillation in temperature, ozone, and tropopause height, and especially the oscillation in tropopause height and can have influences in the troposphere. So the QBO is also important because it influences the residual circulation, temperature, and especially chemical transport. So when you have strong shear zones in the stratosphere that can create transport barriers. So depending on the phase of the QBO, the transport in and out of the tropics is affected. And probably the most common effect of the QBO is on the polar vortex. So often people refer to this as the Holton-Tan mechanism. So I have figures here from Anstey and Shepard 2014 compositing westerly QBO minus easterly QBO. So that's usually done by taking the 50 hectopascal zonal mean wind and looking when it's westerly. And what this typically correlates to in observations is a stronger polar vortex. And along with that, if you're in a westerly QBO phase, then you expect to get a positive North Atlantic oscillation all the way down to the surface. So that's probably one of the largest effects that people look for from the QBO in the tropospheric climate. And I'll talk about this a little bit later, but there's also strong observational evidence of the quasi-biennial oscillation influencing the Madden-Julian oscillation, or the MJO. Okay, so what does this look like in E3SM? So again, here I've taken the 5 south to 5 north zonal mean wind. The top panel is ERA interim. This middle panel is the atmospheric model, so just an AMIP simulation, or EAMV1. And the bottom panel is the coupled run, or E3SM, the one I call it here. And what you see without any fancy analysis is that the period of the oscillation in the default model is much shorter than an observation. It averages out to about 18 months, and it's pretty similar between the AMIP and the coupled simulations. And the amplitude is also much too strong. So especially if you compare the amplitude of the westerlies, it's much stronger than ERA interim. Okay, so a little bit how needed to model the QBO appropriately in a climate model, and how is it forced? So it's forced by a combination of waves, and some of them are resolved in models like Kelvin and Rossby gravity waves. So they're generated by the large-scale patterns of convection and variability in convection. So they're convexively coupled waves that propagate upwards, and they break in the stratosphere and the shear zones, and then drag the shear zones down. And Kelvin and Rossby gravity waves are often underrepresented in models, so that's one reason why it's difficult to get a QBO. Then you also need small-scale gravity waves, which provide about 30 to 50% of the momentum that's needed to drive the QBO, and they have scales from 10 to 100 kilometers in the horizontal, so they have to be parametrized in most models, especially if you have horizontal resolution of 100 kilometers, you need to parametrize these waves. Vertical resolution is also needed in order to propagate the Kelvin and Rossby gravity waves upward correctly, as they can have vertical wavelengths as short as 3 kilometers. So then you need, usually people find that you need about 500 to 700 meter vertical resolution to get a QBO. And in E3SM, that has been taken care of in the troposphere. So when the model was designed, I think Phil made the decision to keep 500 meters all the way through the free troposphere into the lowermost stratosphere, and after that the resolution decays pretty rapidly, and I'll come back to that point. But at least in the free troposphere and lowermost stratosphere, the resolution in E3SM is quite adequate. And then also the dynamical core can be overly diffusive. So for example, the FV dicore tends to diffuse any upward propagating waves really quickly, so even though if you're generating them, you may not be getting them all the way up to the stratosphere. But with the SE dicore and E3SM, I think this is not really a problem. So these bottom two aspects are taken care of from the design of the model. So I'll spend most of the talk talking about the Kelvin and Rossby gravity waves and then the gravity waves. So starting with the resolved waves, these are the typical Wheeler-Colades diagrams of symmetric in the top row and anti-symmetric waves. And the left panels show trim observations. And what you expect is a lot of power in these eastward propagating modes, or the Kelvin waves. And there is an MJO signal here at the small wave numbers and small frequencies. And there's also some westward propagating waves, so Rossby gravity waves, etc. So the middle panel shows an E3SM EMIF simulation, and the right panel show E3SM coupled simulation. And you see that especially the Kelvin waves are quite deficient in the model. And where you have power, it's a little bit at higher frequencies than in observations. And they're a little bit even more deficient in the coupled model than the EMIF model, but this could be just, they're slightly different, but the pattern is similar. There are westward propagating waves, which is good, and they're comparable in magnitude to observations, but the deficiencies in the eastward propagating waves are quite obvious. And also in the anti-symmetric component, you see a similar thing, that there is just not a whole lot of power in E3SM. So there's only, if you're missing the forcing from resolved waves, we can compensate for a little bit of that with parametrized gravity waves, but one choice we made is not to overdo that in this exercise that we did, as other changes to convection are coming, so there will be hopefully improvements in the resolved waves in the future versions of the model. Okay, so what about for parametrized gravity waves? So E3SM takes the Linzen 1981 gravity wave propagation scheme. That's the same that CSM is using. And basically what that does, it takes the input of waves with prescribed momentum flux, and these waves range with phase speeds from -40 to 40 meters per second, and they propagate upwards in a column, and it will deposit a momentum to the mean flow, either if they reach a critical level, meaning that their phase speed equals the background wind speed, or if their amplitude gets too high, and then they break and also deposit momentum. So that's the propagation scheme, and there are two non-orographic wave sources, so front and convection, and this is what's in observation dominant sources of gravity waves. Fronts for the QBO are pretty irrelevant because they mostly are contained to the mid-latitudes. So since the waves are propagating in a column, that forcing goes poleward of 30 degrees, so it doesn't influence the QBO. But convection is the key source of these waves that impact the QBO. So for the convective source spectrum parametrization, E3SM uses the Barris et al. 2004 parametrization, which is a parametrization I wrote a long time ago for my PhD thesis, and is based on linear theory of wave generation by a thermal forcing. So this little cartoon here shows the simplified version, that we assume that convection consists of this large heating cell, and that heating oscillates with a given frequency. It has a height, so that reaches typically in the mid or upper troposphere, and we assume a horizontal scale for this heating. And when this heating is oscillating, so with a given frequency, it generates waves that propagate to the east and to the west. And the dominant phase speed of these waves is related to the heating depth. So the deeper the heating, the faster the phase speed of the waves. And how we get this out in a model is we tie this to the Zheng and McFarlane convective parametrization. So we look at the heating profile without that parametrization, and the deeper the heating, and that number directly goes into the parametrization. So the good part is that the gravity wave parametrization is consistent with the convective parametrization. And that is also the bad part, as every bias in the Zheng and McFarlane parametrization will be carried all the way up to the stratosphere. But at least the model is being self-consistent. And the other important aspect is the wave amplitude. So the wave amplitude by linear theory is proportional to the heating rate squared. And this heating rate ideally represents the heating of the convective cells. However, in the model, we only get the Zheng and McFarlane heating average over the GCM grid box, so which is a much lower heating rate than you would expect in a convective cell. So then the parametrization has this tunable parameter called CF, or the conversion factor, from a grid cell average to the representative of a heating cell. And this factor by default is set to 20, meaning that 5%, we assume that 5% of the GCM grid box is covered by convection. And this number was first picked by me when we were implementing this scheme in a 2-degree version of Wacom, and that's the number that originally ended up in E3SM. So that was tuned for a 2-degree model. And then there is another parameter called the efficiency, and what it means is how efficiently is convection-generated gravity waves. So if you have convection happening, does that mean that 100% of the time gravity waves are generated? Typically not, because convection has a cycle. So it initiates, then matures, and then decays. So it's a fair game to set this factor somewhere between 0 and 1. And that's just a tunable parameter. So by default, this is 0.4, so meaning that 40% of the time these intense gravity waves are generated. It equally could be 30 or 50% of the time, and probably sometimes 1 is correct and 1 isn't, but right now it's set as 1 number. So although the parametrization, tries to tie the gravity waves to something realistic in the model, there is some room for tuning, and this is kind of what we've gone back to and looked at what can be adjusted in order to make the QBO more realistic. Okay, so on the left are the plots I already showed you, original version 1 of E3SM and E3SM. And by default, this conversion factor was 20, and efficiency of the waves was set to be 0.4. So Jack has done a series of runs changing these parameters, and I can't say that there is a particularly good way to do it. You just have to try a few things until and watch how the QBO changes. But eventually, we ended up with parameters CF of 12.5. An efficiency of 0.35 that seemed to give us the best match to observations for the QBO. So you see the modified, the mod GW are the simulations with the new parameters for both the atmospheric only model and the coupled model. And the one issue that we had changing these parameters and tuning is we could not get the easterly phase to get better. So although you see now that the period of the oscillation is much closer to era interim, the period is about 27 months, the easterly phase is a little bit weak in amplitude still. And again, we can't fix everything with the parametrized gravity waves, nor did we want to overtune knowing that there's other changes coming to convection. So we thought we'd stop here. We feel that the QBO is improved, but there is still room for growth, and we'll keep watching this as other changes to convection happen in E3SM. So a little bit on more formal metrics. So the top panel here shows the power spectrum of the zonal mean wind at 50 hectopascals. And era interim is in black. So you see in observations, there is a pretty sharp peak at 28 months. Well, but you also see that it's not the only period, right? So it's actually a broad peak around 28 months. And there are no shorter periods than about 22 months. So the original EAMV1 and E3SM-V1, you see there is a peak at about 16 months. And in a coupled model, it's in a coupled model, in the atmospheric model in dashed here, there are actually two peaks, one about 15 months and one about 18 months. So clearly not very realistic. So in the new simulations, they're shown here in red, the QBO period is about 27, 26 months, and that's in the atmosphere only simulation. And when we go to couples, the period shifts a little bit closer to era interim, but as you see already from the spectrum, the amplitude goes down, and it's partly because the periods are just a broader spectrum, so you have, it's not as sharply peaked. Okay, and the bottom two panels show you QBO amplitude, and I'm looking at two sets of period ranges, so one range from 20 to 40 months, which is really where the observations have the QBO in that range. So you see we've improved the amplitude, so the red lines are the new simulations. They're much closer to the black line of era interim, but the amplitude is a little bit deficient, and that's again due to that easterly phase being a little bit deficient. And the bottom panel shows just the total amplitude in between the periods of 5 to 40 months. And what the blue lines show you is this strong amplitude that you were seeing in the time series plots, the real strong westerlies that were much stronger than the amplitude of era interim. And the red lines, the new simulations, compare much better to era interim. And you may wonder why there is differences between the coupled and the uncoupled model, and that's again due to the changes in resolved waves, and also due to the changes in the parametrized waves, which go along with any changes in sea surface temperatures that are between the AMIP and the coupled model. So that's the upside and the downside of the parametrization being coupled to convection. If the model is producing too strong of ENSO events, then the gravity waves will also be kicking up too strongly, and it will drive a shorter QBO period. So it makes the model more consistent, but it is also a little bit more difficult to tune, as all the biases in the troposphere will carry straight up into the stratosphere. Okay, a little bit on QBO driving. So on the left panel, note that there is a different color bar because the gravity wave drag in the original version of the model was so strong that the accelerations in the shear zones were reaching about 1 meter per second per day, which is about twice as strong as we think that these accelerations should be. But what you see from comparing the top panel to the bottom panel is that in the original version of the model, the oscillation was largely driven by parametrized gravity waves, and the contributions from resolved waves, which is in this bottom panel, is the EP flex divergence, the values are much lower. And especially what you see is that the yellow and the red colors are missing from this bottom plot, and that's the absence of Kelvin waves, which are just not being generated efficiently, E3SM V1. So on the right-hand side, we have the momentum budget from gravity wave drag and EP flex divergence for the new version of the model. And the gravity waves are still dominating, and especially in the positive side, so the positive or eastward accelerations. However, you are getting negative accelerations from mixed Rossby gravity waves in the model, which is good. And you see a little bit along these some shear zones contributions from the Kelvin waves, but they're really small. It's about 0.1 meters per second per day. So again, ideally, I think if the convection is improved, these accelerations will become more realistic. Another aspect that we haven't had time to explore is the impacts of the vertical resolution in the model really rapidly decreasing in the stratosphere. There has been some work by Marv Geller who has shown if you don't have adequate vertical resolution in the QBO shear zones, then the contributions from the resolved waves will also be diminished. So that could be also part of the reason. But since we know the waves are not really being generated in the troposphere as they should be, then we didn't go down this line. Okay, this is just a figure comparing the new QBO, the improved QBO, to other high-top models. So this is a figure from Bushel et al. 2019 that's in review, which is a paper number 1 out of the QBO initiative, or the QBO comparison, which looks at QBOs in multiple models from across the world. So the UMGA7, for example, is the UK model, MRI, the Japanese model, Mirac, another Japanese model, LMDZ, the French model, ECM, German model, and the NCAR models, AGCM3 Canadian model. But what you basically see is that this new QBO is right on par with the other models. They all have their features. For example, ECM5-ish is really top-heavy and has a strong westerly bias. Some of the Japanese models, the phases are not coming down far enough to 100 hectopascal. So really, there is no perfect QBO out there, and the changes have made the QBO and E3SM be a lot more in line with what other models are having. Okay, so you may wonder what changes in the circulation model have occurred after we changed these gravity wave parameters, and it's summarized really in these two bottom panels. It's the DJF, zonal mean wind, between the new simulations and the old simulations, and on the right-hand column is the temperature. And as expected, the changes are primarily in the stratosphere, especially in the QBO region. So where we had a bias, a really strong positive bias relative to air interim, the bias has been now reduced. And similarly for temperature. So, and very little changes in the troposphere. So there's very little changes to the model in the troposphere. Here's a plot summarizing changes in variability. So top left panel shows the DJF standard deviation of zonal mean wind for air interim. Again, you see the two modes of variability primarily in the tropics. There is a lot of variability, and in the extratropics in the northern hemisphere. And in the original version of the model shown in this top right panel, there was too much variability in the tropics. Now we have a little bit too little, and that's again due to that easterly phase being a little bit too weak. But mostly we've changed things in the stratosphere and no substantial impacts in the troposphere. Well, there's some modest changes in the troposphere. What I'm showing here is sea level pressure and surface temperature changes. And the bottom panels show the difference between the modified simulations and the default. And the black contours are areas where are significant at 95% level. And this is based on 30-year coupled simulations. So you see there are very small regions of where the changes to the surface are significant. I think that's mostly in mid-latitudes in the northern hemisphere. And some of them aim to reduce the biases that were existing there, and some of them increase them a little bit, but the changes are pretty small overall. And they could be just, partly sampling issues only based on 30 years of simulation. One more surface change. We have found this we weren't really expecting, but this is showing the standard deviation of sea level pressure in DJF and JJA. And this bottom panel shows the difference between the new simulations and the default model. And you see that there's a huge increase in the variability in the southern hemisphere. And we have not explored this a whole lot, and I can't say that we truly understand it. But that may be one feature to watch if it remains once it's coupled with other changes. There is also a decrease in variability in the Pacific region, so right off the coast of the United States. And if you look at what it is in air interim and in default model, this seems like this change is in the right direction. So in the default model, there was a little bit too much variability in the Pacific, and now we have reduced that. And the changes in June, July, August are very small. So I'm going to go back to this point of the QBO impacts on the MJO, because I think that's one of the things that, being that E3SM has a good, reasonable MJO, that might be nice to look at, and we don't quite have enough years. But this is a figure from Sun et al. 2017, which shows the MJO band filtered OLR for DJF. And on the right-hand side is the variance of this. So this is 30 to 100 day bandpass. So you see a lot of variance in the maritime continent where the MJO is. And what they've done is they decomposed this between easterly and westerly QBO years. And that's shown in the bottom right panel here. And you see that in observations, you have a lot more variance in that MJO time period in the maritime continent in the easterly phase. So we were curious whether we can see this in E3SM. However, right now we're a little bit inconclusive, and it's partly the DJF OLR variance bandpass in that MJO region is really high. So the MJO variance is much higher compared to observations. So when we try to composite East QBO minus West QBO, it's really, we're not getting a clear signal. It's kind of a little bit a combination of positive and negatives. And this is only based on 30 years of simulation. Well, so are the observations, but right now we're not getting a clear signal. So it could be that the QBO is not perfect, could be that the MJO is not perfect, and the combination of that is just not showing a signal. But we're trying to look into a little bit more. Here's another MJO figure. So observations is on the left. So this is the propagation from phase 1 to phase 8. And middle panel is the default E3SM, right panel is modified. And there is an inkling that there is stronger MJO in phase 5 to 6, but this may not be statistically significant. So again, more simulations would need to be carried out to determine the significance of that. But there could be some interactions that are happening. Okay, so in summary, we improved the representation of the QBO in E3SM v1. The QBO period and overall amplitude are now much closer to observations. However, the easterly QBO phase is still deficient, and we largely think this is due to the underrepresentation of Kelvin and Rossby gravity waves, which will be improved in future versions of the model. And as a result of these changes, there have been very modest changes to the mean and variability of the overall simulation. And all of this is documented in Richter et al. 2019, which is going to press sometime soon. The paper was accepted earlier this week, so it should show up in the next couple of weeks. So as a team, I guess we'll monitor changes to the QBO as convection parametrization changes happen, because it all will carry up into the stratosphere. So other teams working on this work convection will impact the QBO. And we're looking at the QBO-MJO interactions, but again, the MJO is not quite right, so it makes things a little bit difficult. And just one slide on future work. So as a team, we're going to move on to improving the momentum transport within convection. That can also change the generation of Kelvin and mixed Rossby gravity waves. And largely, we're doing that by running WRF simulations that will serve as the closest as we have to observations, and we'll do some nudge simulations to compare the in-cloud momentum transport and also add a mesoscale convective transport parametrization that's getting implemented right now. All right, so I think it's right about 10 o'clock, so I'll stop here and take any questions. Thank you.